having it all. Can software be performant, portable, and productive? So I actually have two roles, one at the Met Office, where I look at developing models for the Met Office, and I'm also Associate Professor of Computer Science at the University of Reading. So the outline for my talk will be introduction and motivation, followed by a description of our domain-specific language that we're using and how that links up with OpenACC. I'll tell you a bit about the Met Office next generation modeling system, which is called, for the atmosphere, is called Gung-Ho and LFRic. I'll tell you a little bit about Cyclone, our domain-specific compiler. I'll also talk a bit about NEMO, the ocean model, and some of the physical parameterization schemes. And I'll conclude with some remarks on parallelism in general and programming model standards and where we might look to go next. So if we're going to write some software, write some scientific software to solve a maths problem, we need something to do with it. We need a programming model. And so an example of a programming model is Fortran. You've all heard of Fortran, right? Over here is some Fortran for you to enjoy. And it's a high-level language. It's an abstraction of the numerical mathematics. And the implementation and the architecture of the computer is hidden. We don't see that. The Fortran itself is just some code, is just some text which conforms to the semantics and syntax of the language definition. And then we have a compiler which transforms the code into machine code for specific processes. So we have what we call a separation of concerns between the abstraction of the numerical mathematics. So that means in some sense we can write code which looks like the maths, and the implementation and the architecture is hidden. Okay, so this is the concerns we want to separate. So this is a really nice programming model, and it's a really great way of writing a science or maths problem. However, we break this abstraction by all the parallel and performance and memory features that we have to expose to get the performance that we need to run fast enough to solve the problem. And then we have to hack it all back together again with MPI, OpenMP, OpenACC, OpenCL. It's a whole long list of things. And as you can see, I've had to make that font smaller because people keep inventing new programming models. And not only is a whole list of these programming models, they're all different sorts of things. They're libraries, there might be languages or language extensions, they might be directives or compiler specific directives. So this is all very difficult. So, you know, at the top here is the API I wanted. It's a nice simple programming model where I can just write some code which looks like some maths. And this is the one I've actually got. And not only that, I don't know what happens if I switch this data 3 over here and press this button at the same time, because the programming models, they don't know anything about each other. And so how they interact might be entirely controlled by your scheduler. So, you know, this is really a dog's dinner. This is not the way we want to be able to write code. So now I'm going to borrow a slide from my colleagues at the Hartree Center who work with us in developing Cyclone. So this is why it's got their logo on. So Sergi Ciso gave me this slide, so thank you, Sergi. And basically what we want to be able to get is the 3 Ps of high performance computing software development. And that's productivity. So we need maintainable software. Many people can contribute different areas of expertise, but it's single source. We just write single source code. And then we need performance portability, because it might be risky to choose one platform. There's many different sorts of supercomputer out there. And we have complex parallel code, complex parallel architectures, complex compilers. This makes for a very complicated optimization space in which single source optimized code is unlikely to actually be possible. So in order to solve this problem, we want to be able to try and separate the science specification from the code optimization. So the Met Office is developing a new modeling system to exploit exascale computing. So we have a whole program called the Next Generation Modeling System, so that's NGM-MS, and the model itself is called LFRic, after Lewis Ferry Richardson, which I shall tell you a little bit more right at the end of the talk. And we want to replace our very successful unified model, which does both weather and climate modeling, and it's successful because it is scientifically excellent and also very good at running on supercomputers. We want to try and maintain that scientific accuracy, but improve some of the features in order to exploit exascale computing. In particular, we need to abandon this long lat grid and the structured mesh that we have for the unified model, but maintain the scientific accuracy and use something like this, which is a cube sphere mesh in an unstructured way, and also improve our ability to exploit other programming models. And so to do that, if we want to get the same accuracy, we have to use a different discretization scheme, different new mathematics than what we were using before. And the time integration is essentially the same as semi-implicit. So I need to tell you a couple of things about the domain that we're trying to solve, because I'm going to be talking about a domain-specific language. So telling you what the domain is kind of important. And in fact, that diagram here this diagram here is not drawn to scale. If I'd drawn it to scale with a 100-kilometer atmosphere, which is about the depth of the atmosphere up to the Kármán line, then it would just literally be a thin blue line around this sphere here. So this diagram here actually has a 600-kilometer depth atmosphere. So the atmosphere is very thin and it's vertically stratified. So already there are some things about this domain which make it special, which is the vertical it behaves differently to the horizontal due to gravity, and the size of that domain is very different. It rotates. It's not in thermal equilibrium. The sun shines and deposits energy on one side of the globe, the spinning round, and it radiates energy at lower wavelengths at the other side. There's multiple components. There's an ocean, there's an atmosphere, there's ice and sea ice and land surface. There's moist chemical and biological processes. So if you want to simulate and solve this system, it's a very complex domain. It's multi-component and multi-scale. The models themselves are large, of order 1 million lines of code. They're legacy in the sense they take very long time to develop, 10 years or more, and they may be around for lifetimes, 25 years or more. They undergo continuous scientific development, and they get used in operations and production. And so when you change them, we necessarily want to be conservative to make sure we get the right answer. So given those things, how are we going to try and solve this, this computing problem that I've just alluded to? Is we're going to try and use develop things using a domain-specific language. Why do we want to do that? Well, as I've tried to describe, there are too many programming models with a rapid evolution of diverse hardware. And so we end up with the parallel and optimization code polluting our science code, which makes it really hard to develop the science code. So how are we going to do that? Well, we want to restore the separation of concerns between the science and maths code and the optimization code and things to make the code go fast. And we can do this using a layered software architecture, which is what we have here. And so we have algorithms at the top, which are a high-level description of what we're trying, mathematical description of what we want to do. At the bottom, we have kernels, which are implementing particular mathematical operations. And in between, we have the parallelization system. And if we do that, we can use a code generator or a Python application called Cyclone, which can parse the Fortran code, do transformations, and generate the parallel code for us. And it has its own intermediate representation. So if I tell you a little bit about Cyclone, so this is mostly developed by colleagues at the STFC Hartree Center. So that's Rupert, Andrew, and Sergi. And so this is why I'm using their slide again. But we're kind of co-designing the DSL between the science developers at the Met Office and the people developing the code engine at STFC Hartree. But also people from the Met Office get involved, particularly Eva, myself, and there's other people, Jorg from the Australian Bureau of Meteorology as well. So what does it do? It's a domain-specific compiler for embedded DSLs. In our case, it's embedded in Fortran. It's configurable, so there's different front ends. So you can look at the NEMO front end for the ocean model, a finite element front end for LFRic, and it has support for distributed and shared memory parallelism. It supports code generation and code transformation. And we think of it as a tool to be used by HPC experts. And so the optimizations are encoded as recipes rather than baked into the scientific source code. And we can then have different recipes for different computer architectures. So this means we can have scriptable whole code optimization. How does it work? Okay, well, typically we start with our Fortran code, which is with the embedded DSL, with the assigned domain knowledge that we want to exploit, which we have to code in a particular way. And for LFRic, we're using Fortran 2003 object orientation to control that API. There is the DSL front end for Cyclone, which knows how to read that DSL information. That generates its own intermediate representation, the SciIR. We can then do transformations on that SciIR to change what it's going to do. And then we can go to the code generation where we generate, in this case, a Fortran backend to generate some more Fortran code, but we can also generate the parallel code as well. What does that look like? Well, here's some more Fortran. Here is some algorithm code that that we use in the LFRic model. And so you can see it's just a Fortran subroutine called invoke. And so then we have some types, which is a kernel. What are you going to calculate? And you're going to calculate, execute this thing on these fields. And you can have another kernel with some more fields in. And so invoke is part of the DSL. It just kind of means do this in parallel. Kernels themselves operate on a single column of data. The fields here are global data parallel global fields. They're global objects. And we can have multiple kernels in a single invoke, which gives us scope for ordering and parallel communication, etc. So the key to making this all work is what happens in the kernels. So in the kernels themselves, they encode the mathematical operations we want to do on the fields. But when we write them down, we already know more things about what it is they're going to do computationally than typically you can express in Fortran itself. So we want to capture that rich domain-specific information. In this case here, we want to be exploiting the parallelism for over horizontal looping. And because we've written down some things about the horizontal loop, we're going to be looping over cells. We've got some things called data access descriptors that will tell Cyclone which fields are going to be read from, which ones are going to be written to, which ones are going to be incremented in this case, and which fields are on the same of these finite element spaces and so will share looping structures. And because we know all this, basically we write it down. That means when Cyclone reads this and parses this, it can then make some decisions about when it's got to do a halo exchange, for example. And so this is doing a matrix vector operation, and the horizontal looping is controlled by the Sci layer. The kernel itself looks pretty simple. It's just some Fortran 90 style code with some arrays, and some loops, basically. What does that look like inside to Cyclone? So this is the internal representation that we printed out here. And so you can see you've got a list of invokes when you're going to do different calculations. You've got loops, what are you going to loop over? And then here's something called a built-in, which means with something that Cyclone is going to generate the kernel itself. It's going to do a halo exchange. Here's some more loop. What is it looping? What is it going to loop over? And here's the actual kernel code itself, this vector matrix code I was talking about earlier. Here, that's where that kernel is going to be called. And then there's another loop. And we also have a global sum at the end, for example, in this particular part of the calculation. If we did some different transformations and looked at doing Cyclone intermediate representation with OpenACC, this is what we would see. This is the internal representation of intermediate representation of Cyclone. And so now we have a data directive. We're going to enter a data region. Okay, we might still need to do a halo exchange. Now we're going to do things in parallel, and so the loop can be done in parallel using OpenACC. So the loop's still there, but we now have some OpenACC type directives we're going to do first, and then there's the kernel code down at the bottom again. So what does that look like when we generate the actual code? Well, here's some OpenACC directives for copying some data to the GPU. And then here is an OpenACC parallel loop. So we're using kernel offload in this case for LFRic with explicit data movement. We're using the parallel looping structures. And then in the actual kernel itself, we might want to do something in the virus vector to get the vectorization to work as well. So that's the ACC loop vector. And we're taking advantage of the fact that we know this is a vertical loop. And so we can know some things about the dependencies, about when we might need to do things. But we need to insert an atomic update in order to get the right answer there. So what's the current status of OpenACC for the MetOffice model LFRic? Well, we can generate some, well, perhaps even most of the necessary OpenACC instructions that we need to run with some handwritten stuff going on in kernels. We can't quite do everything yet, but that's something we're working on. So this will run and give the correct answer. But currently it's not very quick. We're doing too much data transfer, which we need to reduce. And we haven't really done very much with any real GPU optimizations yet. So that's the next stage to get the thing to run faster. So we can have single source science code, generate some OpenACC to get the whole thing to run on the GPU. And now we're going to look to optimize to make it go faster. So regarding the data movement, then the logic for the data movement is kind of the same as the halo exchanges. And Cyclone can already exploit that domain-specific information. And if that means if that turns out that we're still doing too much data movement between the CPU and the GPU, the alternative would be to run the whole model on the GPU and then just occasionally come back to the CPU when we need to do other things and do it that way. We're exploring both those options. We're looking to develop memory and loop optimization. So these are actual code changes to the kernel, not just adding directives as well, which is something we can do, but we haven't looked at what we might do for the GPU yet. We can do things like kernel inlining, where we lift the kernel up and put it actually in the SI layer. And so we don't actually offload a procedure anymore. And then we can look to fuse loops together, exploit reduced precision. But the whole time we want to maintain single science source code and generate all these OpenACC optimizations. So that's as far as we've got so far with LFRic. So I'll tell you a little bit more about NEMO, the ocean model, which is used by quite a few centers. And I'm going to be reporting here work from my colleagues at STFT Hartree Center. So this is GPU offloading for single node. This is the speed up compared to Intel, a 6-core Intel Xeon. So it's single node only. It's not a very powerful Xeon, but this is just illustrative of the kind of things we can do. And here in this case, lower is the time per time step. So sorry, it's not speed up, it's time per time step. So lower is better. So this is the original code on a single node using MPI to use all the cores. With some OpenACC we've put in, we can now run on a GPU, and it does go a bit faster on the GPU. Well, we can also try and do OpenMP as well, and that seems to go a bit faster. And then if we do a few extra things, we can get it to go much faster again with the OpenACC. So for the NEMO code, we're using OpenACC kernels, directive, and managed memory. And this works very well for NEMO because there are no complicated derived types, so that this simpler structure works better. The OpenMP here is actually is faster because we're doing things in a more explicit way, including some code change, not just directives. And if we did that for the OpenACC, we're pretty confident we would see a similar speed up. The manual tweaks to get it to go this fast down here are actually NEMO itself replaces some of the Fortran maths intrinsic functions with its own code, and we don't have an OpenACC version of those, so we've had to do those by hand, or in fact the opposite actually, stop it using its own version of the intrinsic so it will run on the GPU. And of course, we can try and do the whole thing across multiple nodes, and this is looking really, really good. So I think we have a warning here. This is work in progress, but this is looking at running multiple GPUs. The black is kind of like the baseline running on Intel CPU sockets only, and then we're comparing that to different optimizations we've done for GPUs. So we started off, we got it running, it wasn't scaling with multiple GPUs, it wasn't scaling, it wasn't running very quickly. We increased the amount of optimizations we can do, for example, using GPU Direct, and then we thought it improved performance, but the scaling still wasn't great. And then finally changing some of the things we were doing with the Halo exchanges, these manual tweaks here, that we actually get much better scaling up to 100 GPUs and actually go much faster than the Intel Skylake. So that's a really good story. And again, this is using single source science code and generating the OpenACC. So finally, another project we're doing is we are working at the Met Office with Oak Ridge National Lab, who are working with us on behalf of the US Air Force, which is Met Office UN partner. We're looking at two of the physical prioritization schemes, one of which is the radiation code called Socrates, and there's another one called a microphysics code called Cassine. And so these codes can run with standalone drivers, they can run in the UM, and they can run in LFRic, and they do particular physical prioritizations, like, for example, the radiation, so that's sunlight heating the model, or the microphysics code. And this is work done with people at Oak Ridge. So to start with, we are looking at how we develop what kind of code changes we need to do. So we're doing this by hand to start with. Ultimately, we will look to use Cyclone, but first of all, we need to see what should the code look like. We're having to do some refactoring to move around where the loops are, so that instead of having looping looks like this, and so we start doing OpenACC parallel and then have to stop because something has to be sequential, is to move the loops around and try and combine them together to get lots of work for the GPU to do. Once we have this and we have the performance, we'll look at what the API should look like so that people can write the single source science code, and then we'll look at developing the transformations. But at the moment, we're just seeing what do we need to do to the code to get it to run on the GPU. And if we do those things, we get some nice speed up. This is running on Summit, comparing a single socket with with the single socket's worth of GPUs. And if we make the problem nice and big for the GPU, we get quite an impressive speed up. This is really nice. but of course, depending on which GPU you're comparing to which CPU, tell a different story. So this is running on a different machine. This is where this is actually the US Air Force production machine, which has got the AMD processors, which are much more powerful. So the baseline gets faster. So the speed up with only 2 GPUs looks less impressive. But there's different complicated performance story to tell there. But the point is, we can run the whole thing on multiple GPUs. So that's looking nice progress there as well. So there's kind of multiple thrusts that we're trying to do. So I'm coming to the end of my presentation now, and I just thought I'd conclude with a few remarks about parallelism in general. And yeah, parallelism and peering into the future. What should we do in the future? How should we write parallel code? And are DSLs the answer? And I think a really important part of that is to think about for what and for whom. For the Met Office, for now, they represent a really good choice. We are having to develop a new modeling infrastructure. So whilst we're doing that, we can also develop the DSL. And this allows us to mitigate the proliferation of different programming models and have the code be both performant and portable to different programming models, whilst we can maintain the single science source code, which means the scientific developers who are developing the model can be productive. So this is a good choice for us. But if we're going to do that, we have these 3 Ps come with a cost for us. We have to develop and support the DSL. Now, for the Met Office, we can decide to do that because we own our own DSL and we're a big organization, so we can make that choice. So for us, it's a good choice. For other people doing different things, it may not be such a compelling, a good choice. But for us, certainly it is. How should we express parallelism in general? Well, there's been quite some developments of parallels into the high-level languages themselves. There's been developments in C++ and the extension into SYCL, which is hopefully coming back into C++, that will enable parallel things to be done in the language itself. And there has been some developments in Fortran as well, both co-array and now with do concurrent. So you could just write the whole parallel code in your own high-level language. But then we come to the more difficult question is are they general enough? But yet at the same time, are they specific enough to exploit some of the architectural features the parallelism needs to exploit, and at the same time as being general enough to be able to write any of the maths you need to write in these structures? Because actually what we have is a hierarchy of parallelism we need to exploit. We have distributed memory, shared memory, and on something like a GPU, we have a hierarchy of parallelism even within the GPU itself. And if we're using the structures we get from the high-level languages, does this allow us to get us back to this separation of concerns? Because if it doesn't, or if we can't, essentially they're just another programming model. And then effectively we just need a new backend for the DSL to target this particular programming model embedded in the high-level language itself. Contrast to that is the specific programming models, for example, like OpenACC, which whilst it is a programming model specification, it looks at a particular, you can do general things with it, but in general, it's looking more at GPUs. And so it's natural to program those architectural features using something like OpenACC, because that's primarily what it's developed for. Because it's not general, because it is specific. And if we're using a DSL on top of that, if we've raised the abstraction, it's really simple to annotate our source code with directives. And it's a really nice way of programming. We have some extra information that we know, that means we can make the right choices about those directives. And it's a very nice way to tell the compiler what to do, because then we don't have to actually change the source code. Although typically in the end, we ultimately do, it's actually a really nice way of coupling things to the DSL. So finally, then, the final point on this slide is really what the important thing is: the separation of concerns between the parallel, what is the science domain, and making things go fast. And what I want to say is that I think really parallelism is something that's very inherent to the problem domain, and I'm going to tell you that out of my last slide. Whereas architectural features belong to the implementation domain, for example, to the compiler. And so, for example, it's really hard to beat compiler-generated caching behavior. I mean, you can, but you have to work quite hard. The compiler typically knows a lot about the architecture and can do caching really well. And so if you want to beat that, you've got to do a lot of work in the code to get there. Whereas in comparison, parallelism you're expressing the parallelism that comes from the maths. And as the example of this, I want to go back to Lewis Fry Richardson. So Lewis Fry Richardson attempted to do the first NWP calculation between 1916 and 1918, whilst he was a volunteer ambulance driver on the Western Front. And he tried to do the calculation. It took him a long time, 2 years, to do like 2-3 hour time steps, and he got the answer completely wrong because he had bad input data and he didn't know some maths about what's called the CFL condition for fluid dynamics. But in 1922, he published a paper about weather prediction by numerical process, where he recognized that the problem was parallel. You could do it with, say, 64,000 computers. And in 1922, 64,000 computers was a room full of people. Here they are. There's nothing about the machine. The parallelism is all to do with the maths. And so to get that separation of concerns, I think is really important. So in conclusion, then, we are developing a domain-specific language using a domain-specific compiler, which we're co-designing, called Cyclone. Met Office model is developed so it can be performance portable and productive. So I am hopefully having it all. But we have to develop and maintain this DSL in order to do that. And then the model can then be developed in the DSL. If we do that, we can target specific programming models, for example, OpenACC for GPUs, and then we can optimize for that architecture, which I think I've shown you we've had some success in doing, but whilst maintaining our single source science code. And then finally, I made some comments about how do we express parallelism, thinking about ideas of domain-specific languages versus general purpose languages versus multiple programming models. So with that, I conclude my keynote presentation. Thank you.